With that, I would like to welcome Dr. Rob Stephen on the podium. A quick introduction on Dr. Rob. Dr. Rob is a master specialist within group technology in ESCOM. He is the Cigre president, and he is the first South African to be elected a Cigre president. And that is the role that he is currently holding. Thanks, Dr. Rob. Welcome.
Good morning, ladies and gentlemen. Thank you. I'm Rob Stephen. I'll be covering a little bit of load modeling from the past when we started it for the electrification program in the 90s. And then give you a little bit more about what's happening and around the world and stuff like that in the future. So at the start of the electrification program, we really didn't have a lot of information on rural dwellings or loads in the rural areas. What we had was a sort of standard low-cost housing was around 3 kVA per house. And that's how we normally did our reticulation design with a 300-meter radius for a transformer zone. So 100 kVA, normally standard transformer zone, 300 meters. And once you started applying that to rural areas, it actually became incredibly expensive because now you couldn't even do the 300 meters because houses weren't even 300 meters together. In high-density areas, it was fine, but in other areas, it was really impossible. So our initial load research allowed our ADMD to drop down, right down from 3 kVA, some cases around about 0.4 kVA startup. And we were designing 0.4 kVA and 0.6 kVA on average in a lot of the deep rural areas. That allowed you to really go fairly long. There was some consultants designing 900-meter diameter transformer zones. So this actually dropped your cost per connection phenomenally. And this is one of the important factors of load research so that you can design appropriately. Otherwise, you really can start putting really expensive networks down, which actually affects other people who then don't get connected because there's no money. The parameters we found initially were linked to house size because we didn't have growth. But nowadays you can get its growth, house size, and income per household. That excludes the sort of migrant areas in the area. In other words, you design one house per one stand, come back 3 years later, and there's 10 houses on the one stand. So that's also a growth, but it's a different kind of growth. There was also research that done a lot with Ron Herman and Trevor Gaunt, looked at a sort of constant current model. This might change in future. If you've got a lot of power electronics on the network, you might go to constant power models, especially with the electronic voltage regulators. Now, this was one of the very first results that we got out of an average household. You can see the variation in the points, and Marcus got this graph. How he actually got a line here was quite artistic. But he managed to put this sort of as an envelope. And you can see that what we were trying to deal with, let me kill this, sorry. What we were trying to deal with was something which was quite variable, and we didn't really know. So we had to make some guesses. As I said, the 0.4s or 0.6s. And then we try to verify that in future years going on. This is the data from 2006, so now that's, 22 years later. 24 years later, each is 60 consumers for 1 year. Now you can start seeing your average winter load and your predicted winter load. And you can see that we've now, if this curve is unity, then we're 100% accurate. So we've actually started getting parameters and prediction models in this particular consumer area fairly well. And you can see the things coming in: average temperature, income, time electrified, and floor area. Those are your main parameters in that regard. And these aren't static ADMDs. Of course, you know the beta curve, which Schalk will cover, as to how we actually determine the probabilistic volt drops. This is an example of Butterworth. Monthly consumption, 330 kilowatt hours per month. Income around 7,100 per household per month. And you can see the sort of RDP type, what we call RDP type houses, around about 70 square meters. This is quite clean. If you come to some of the areas in Gauteng, you'll find that between these two houses, you've got about 10 squatter shacks, which are fed either before or beyond meter, which really starts messing your load up. But in this area here, and in fact, most of our rural areas, you don't get that sort of really high intensity migration coming in. You do get houses coming in on extra stands, which you can then plan for. This is also something to look at, which is the climatic zone, your temperatures. And you'll find this is in Butterworth. These are normally waking up in the morning, coming home at night. But you can also find that you'll find uncertainty due to cold fronts, for example, in the Western Cape, where you get one week is very low, even in the same season. Next week you get, because the cold fronts come through, you now start getting a lot of heating load, and that starts picking up your load. So that's also a complicating factor in certain areas. That's why it's important to do load research, not only in density in certain locations, but also in different climatic areas. This is a demand estimation which is actually on the SANS 507 NRS 034, and it's for Butterworth, which you can see your load growth over the years. And this pattern we didn't really know at the start. We were just guessing what the pattern would be. But we did, the way to design the networks then was to actually have a robust network so that you can actually expand without a lot of extra cost. So you plan your final design, and then you add in as your load grows. So you can go from 50 kVA to 100 kVA, 315s, 200s on the pole top, going forward for your transformer zones. So just to also state that our load research that we've done, we found was absolutely critical, especially your type of load profile. And this kind of load is a constant current, constant power, constant impedance. What kind of curve does it follow? What kind of diversity factors can you use? Which is also a means of probabilistic determination. And the investments, if you get it wrong, are in the billions. It's not just a few million. If you design at a 3 kVA and you should be designing at a 1 kVA, you can spend a lot of money with underutilized network, or vice versa. And we wouldn't have been able to meet our cost per connections really without this information that we get from the load research. And a lot of our templates, standards, everything has been done based on input from load research. Now, it's important to keep going. The problem is with load research, if you have a gap, it's very hard to fill in the gap of missing data. So you then have to make assumptions to cover the gap. And if you do that, you don't know whether it's linear, whether it's non-linear. How did you get from one to the other on the growth? Was the parameters changed? Did more people come in? Did they change appliances? There's a lot of stuff you don't know. So if you think, we'll leave, we've got enough now, we'll stop it for 10 years and come back, you're most probably going to have to go through a learning curve again of about 3 to 5 years before you start getting accurate results again. So the important thing to say, we've been stressing this in research, is just keep going, keep putting the meters out there so that we can cover the gaps. And what we found a lot with the load research was that normally the data and results came in a year later. So we'd make our decision on the ADMD. A year later, we'd get the results from load research. But at least we had a check. It wasn't as if we were designing at 0.4 and we said, no, hell, we should be designing at 0.8. So it was at least a check. So we could then say, okay, at least the data is late, but it's not a train smash. Now, what's going to happen in the future? The thing is that in the future, and this is not common now, it's very common overseas. In fact, over the way they're looking at it in the States and that, they don't do, our load research is world class. It's right in the front end. They don't do a lot of the deterministic load determination as such. What they're looking at now is appliance use. So what happens when you switch your geyser off on smart housing? If you switch your lights off, if you change your pool motor, you switch your fridge off, how does that affect your profile? And their term for electrification is changing from gas to electricity, because a lot of the renewables now are providing a lot of very cheap energy. So in the day, if you can then switch and do all your heating and storage of heating in the day, that'll help you at night to give you a low overall cost. And so to do that, they're changing from paraffin or liquid fuels into gas and gas into electricity. So that's how they term electrification. So you might see a lot of papers on electrification from EPRI and IEEE. It's actually not our electrification. It's how to change from gas to electricity. So what happens here is that with them, you're getting a lot of PV on rooftops, mainly due to subsidies, which we don't have. But the trend, either way, is going to increase, whether in South Africa or anywhere else, because these costs are coming down. So it actually starts, and with your storage costs, you're actually now starting to get it lower than your purchase costs. So your trend will increase, and what's also going to come in is electric vehicles. So you're going to find that these are just mobile batteries. So you'll find that there'll be charging batteries and discharging batteries, depending on if they can sell to the network or not. So what you're going to find is that your loads, now even if we do all this research, your load doesn't change. The demand normally doesn't change in the house, but how you supply that demand changes. So they could supply that demand from an electric vehicle battery or a PV or whatever. So you'll find that your loads now vary randomly on your network. They can become very high or negative. A negative load is really just a generation with a backfeed. So you could find that now your network, where you thought was radial, has now got a backfeed. You've now got voltages right up where you didn't think you had. And there's going to be a problem with our fixed load, offload tap changes on our transformers, where we design our network for radial feed out. We haven't got the offload transformer. So what you might need now is your electronic voltage regulators or electronic tap changes on these transformers, which is available. You also find your profiles can vary randomly, which doesn't really help us. So not only does your load magnitude vary, but your profiles vary. So we need to be able to model stochastic loads and apply network designs which are robust. In other words, if you do have this, what's going to happen? If you don't have that, what's going to happen? In other words, you can have a network which can take negative loads, can take positive loads, can take varying voltages at any times, and can take PV or any other thing that they add, electric vehicles, which is mobile loads. So it's that kind of thing that we need to bear in mind going forward. But this also makes load research even more important, especially in your areas, your high-income areas, where you're going to start getting your electric vehicles coming in more prevalent than you would in the rural areas. So although we think that we might know at Pretoria we run at a 9 kVA, well, maybe it goes to -3, -5 at some stages. You've got a 14 kVA swing on some of your houses. And your voltages can in fact go quite haywire then. So just in conclusion, load research is still critical to your successful network design. Without knowing your particular loads, where those loads are, what the profile of the loads are, what's their distribution, so that you can get your correct diversity, you can't really do a decent network design. And this load research now will become more important because of the variation that we're going to bring in due to distributed energy resources, electric vehicles, and other things coming in. The other thing we don't have in this country is markets where you can actually bid onto the grid. What they're doing now, especially in areas like Denmark, you've got a house with storage, you can bid that as an auxiliary service to support frequency or voltage. And you can do that at any time. So depending on your market design and how the market tariffs work, your load can vary quite substantially. And it's not just the installed demand, it's actually how they actually use the equipment. So this kind of information is critical so that we know in this particular area with this kind of market design, this kind of distributed energy resource, this is what our load can look like. This is a network that we need to design. So we also need to start looking, the loads will start to become more stochastic. At the moment, we are using a probabilistic design for loads, but in future they will become more stochastic. And really the future is not what it used to be. They're now looking at using blockchain systems for trading. So you'll find that your house, even without a market, they can still start trading with customers in different towns. And it's quite weird how they're actually doing that, but they are starting to see how they can actually do that, which then starts affecting the load and the export and the installation of storage and DER. So really, the future is not what it used to be. But if you want to get into some really exciting stuff, I think load forecasting, load modeling, and Marcus mentioned that at the moment we've got about 10 to the 12 data points. So you need to start looking at big data management on load research. And this is going to get more and more. They're starting to even use PMUs into MV networks overseas now because of the instability of the operation. And then you're starting to get big data coming in. And in 6 months, you can get 10 to the 12 data points. And now you actually start managing all this stuff. So these kind of things are actually getting quite exciting. So you've got some really endless opportunities here if you want to do your planning and load research, etc. I think that's it. Thanks very much.